With Doubtnut, get instant video solutions to all your maths, physics, chemistry, and biology doubts. Just click the image of the question, crop the question, and get instant video solution. Download Doubtnut app today.
Hello everyone, let us start with our question. In this question, what is given that there is a non-conducting ring of mass m and radius b and uniform linear charge density of lambda is given as shown in the figure in a gravity-free space. Now there is also a uniform coaxial magnetic field B naught pointing up in a circular direction of circular region of radius a. Now if this field is switched on, then so what we are doing, we are increasing this. If this field is switched off, so the magnetic field was initially going in the upward direction. Now we are switching off the field. So what will happen? So there would be a EMF which would be generated, okay, and which would oppose this. We can say that switching of the field. So initially, if we switch off this, what will happen? So the magnetic field going up in the upward direction, that would decrease. So there would be an EMF which would be induced in this circular loop of radius b, which will try to increase the magnetic field. So how can it do? If, for example, if it produce a current in the counterclockwise direction, because it need to increase the magnetic field in the upward direction, okay, like this. So if we use our right hand rule, so we can say that if we place thumb in this direction, then only our fingers will curl in the upward direction. That means this is how this magnetic field would be produced. So this would be we can say that this should be the direction of the current, or we can say that this would be the direction of the electric field. So if we see from the above, so what would be this loop look like? So it would be looking like a counterclockwise or anti-clockwise. So we can say that there would be a induced electric field on the periphery of the ring in the anti-clockwise sense as seen from the above. A is the correct option. Now induced electric field imparts angular momentum of magnitude this. So we can check this. For example, if we just make our ring, okay, we just make a schematic of our ring. Let's say this is our ring. So this would be our electric field, okay. Electric field would be circular, okay, in the counterclockwise direction. So we just take a small charge of let's say if this is length dl, very small length, okay, at a distance. What is the distance? It is, we are taking this this ring, so it is at a distance of b. So we can see that this charge would this length would be having some charge, because lambda is the charge density. So the charge here, it would be dq, which would be equals to lambda into dl. Now due to this charge and due to the electric field in this direction, this would be also the direction of the electric field, so it would be having a force. Now due to this force, why there would be a force? Because we know that our force would be equals to, the small force would be equals to dq multiplied by the electric field. This is how we write the force. So that means in this, if we view from the above, so it would be something like this in the counterclockwise sense. That means the force is at a distance from the axis, so it would cause a rotation, or we can say that there would be a generation of the torque. So what is the small torque which would be generated? We know that the torque would be equals to df multiplied by the distance. So what is the distance? It is equals to b. So we just write b. So to calculate the total torque, we can say that we can just integrate this result. So it would be equals to integration, then b df value would be equals to e into dq, and dq we can write lambda into dl. So it would be equals to b into e lambda dl, or we can say that d lambda, these values would be constant. We can just write integration of e into dl. Now we also know that EMF which is induced, the magnitude, it would be equals to, by the Faraday law, we are just writing about the magnitude, it is d phi divided by dt. Now what is flux? Flux is this magnetic field multiplied by the area. Now this would be the area in which we are having the magnetic field. So we are just having a magnetic field into this area. That means pi into a square. So area would be constant. We take it to the outside. So it would be pi a square. Then it would be dV divided by dt. And this EMF, or we can say that voltage, could be written in terms of magnitude. We are just writing integration E dot dl. This is how we can write our EMF. Now E dot dl, or we can put the value into this expression, then our torque would become b lambda, and this value would turn out to be pi a square dB divided by dt. Now we know that angular impulse j would be written as tau into dt. Okay, just we'll write momentum as equals to force into dt, or force into the time. So angular momentum, or we can say that this is our impulse. It is written as tau into dt. So tau value we know. So lambda pi b a square. Now if you multiply it by dt, so it would be dB. So what is angular momentum? It is this angular impulse. It is equals to change in angular momentum. That means it is given as to be LF minus of Li. This would be okay. So just forget to have an integration sign here, because we have just calculated this angular momentum for the small this time interval. So there would be an integration. Okay. Now integration would be from where to where. So initially the magnetic field would be equals to B naught. Finally it would be switched off. So this value would turn out to be 0. So we just first write pi lambda pi B a square. Then integration of dB would be equals to B if you put the limit. So it would be B naught. Even though it would be minus B naught, but we are just taking the magnitude wise. So it would be actually it would be minus. So we just put a minus. Then we will be taking just the magnitude. Now this is change in angular momentum is equals to the impulse, angular impulse, not impulse but angular impulse. So we can just have the value as pi lambda pi a square b b naught. Now initially it would be at rest because it would be started into motion when there is change in flux. So initially there won't be any change in flux, so this would be 0. So LF we can say that final angular momentum, this would be equals to lambda pi a square b into b naught. This is the magnitude. Okay, so we have just written the magnitude. So if we can check our option 2, so option 2 would also be correct. Now the final angular velocity we need to find. So if we know that angular this impulse would be equals to I into omega. So it would be equals to I into omega f. So it would be lambda pi a square b b naught. So from here angular velocity, final angular velocity, this would be lambda pi a square b b naught divided by I. Now this is independent of time. Now in the B option it is given as final angular velocity would be more if time to switch off is small. This is wrong because it is independent of time. And here it is saying that it is independent of time. That means D is the correct option. So A, B and D, these are the correct options. Hope you understood the solution. Thank you.
For class 6 to 12, IIT JEE and NEET level. Trusted by more than 5 crore students. Download Doubtnut app today.